So today we'll cover week 10 and week 11 lectures first, and then we'll go through some problems on the contents. So this is the topic, neural network based controllers in CPS. So week 10 topic is so I'll first go through the slides. So basically here we are we can see that using an artificial neural network, how can we design a control unit for us as a physical system. So to do that, we first need to understand how neural network works. This is very preliminary details about neural network. So just quickly go through them, and so how the a forward pass is works in a normal perceptron. Uh, for that, we'll see if there are multiple inputs. We are basically assigning uh, there are different layers of nodes, and we are so these are basically called neuron and an artificial neuron or perceptron. So this is basically a simple operational unit that in a neural network uses. Using these multiple such units, it forms a big network. So each unit will basically have some weight that it will multiply with the input, and the output will be then passed through an activation function, and the output will be going to the next layer. So this is how each of these units work. So if you see this, for maybe if we consider only one layer in this case, so for one layer, so consisting S neurons, basically this is how, if the input is P, so this is how the output A looks like after going through the weights that is defined for each of the edges that is connecting these nodes, and along with that we have a bias. So with this if the weight and bias, after using the weight and bias, we pass that through a activation function. This is how a weight matrix looks like, and this is our bias matrix looks like. So as you can see, there are S neurons, as I said earlier. So W1 to WS. So there are S many. So from P1 to PR, there are R many perceptrons here, and there are S many nodes here. In each node, from in input layer, there are R many nodes, and from there we are passing each of in input layer there are R many inputs. Sorry, so these inputs are basically passing through this layer of perceptrons, where there are S many perceptrons. So each of them will be, however we are adding it, however we are sending the whichever input signal is being sent to the nodes, that input signal will be summed up by multiplying different nodes and weights. So this is the weight matrix that it uses for that purpose, and it adds the biases with each of the after multiplication with the input, and then it passes it through an activation function. So after it is passed through an activation function, this is how it looks like. So these are basically, since these are basically matrix multiplications, we can use it, we can do it parallelly using some parallel architecture like GPU like architecture. So for M such cascaded layers, we get a feed forward neural network, and the output looks like this. That is basically repetition of the same operation for each of the M layers. So after we get that, a brief idea about how activation functions work. So basically, they are basically used to introduce some non-linearities, activate or deactivate the linear components. So these are a few examples of these activation functions. And if we go forward, so how the weights are updated afterwards, how do we eventually train the neural networks, how we tune the weights of the neural networks, that is where this back propagation comes in. So we have a loss function whenever we are designing a neural network. We have a loss function, and the loss function looks like this, where TQ is the target reference for each of the Q outputs. Remember that we started with R inputs and Q is the number of outputs, and we are basically comparing each of these with the before the output layer, whatever is output from the last set of perceptrons. So from there we have key outputs, so Q outputs. So those Q outputs and what is the target reference output, we are finding a distance between them, a square distance basically. So that is what we are denoting as f of x. So here x is nothing but what we are trying to change here. What are we trying to change here? We are trying to update the bias and the weights of the neural network. So we are considering that as the states of the neural network while we are computing this. So our goal will be to find such a set of weights and biases so that this is minimized. So for that, if we see, since this is obviously a quadratic function, a loss function is quadratic, so it will obviously look like a parabola. So, and this is how it is plotting against x. So depending on how do we want it to, I mean, we have a minima for this, and that minima is what we are trying to find out here. So for doing that, obviously the usual procedure that we do everywhere whenever we are trying to find out if an optimal value that minimizes a certain function. Obviously, we have seen this in optimal control design in dealing LQR. Same thing is applied here as well. So basically finding a derivative. Application algorithm establishes the network parameters of every mth layer in every kth iteration. Kth iteration basically kth iteration of the backpropagation. Every time I'm comparing the current output of the neural network with the target reference, that is one iteration. So for each iteration, this is how I am updating weights that I'm going to use in the next iteration. Okay, so if this is the last weight from the last iteration, and this is what we are updating it with. So this is basically a sensitivity. This is a metric that we call the sensitivity of the loss function. So how do we compute that? Del f del n mi. So what does it mean, del n mi? So here n can be either the weight or can be the bias. So in this case, we update the weights by finding how much change is occurring, the loss, how much change the loss function faces if we change the weight, and how much change the loss function will face if we change the bias. And accordingly, we update the corresponding parameters. That is what we are defining as sensitivity here. So if we have the equation of sensitivity, this is how we compute the equation of sensitivity in mi. So basically, this is for mth layer. That is why we are denoting it with m. And this is for kth iteration, and this is for every I in 1 to q. So remember that q is the number of outputs. So for every ith output, this is how I am computer sensitivity. So this is the for this is the value that we can compute as sensitivity, and n equals to basically this whole value is n. What we are computing using the last layer while we are given an output with the last from from the output that we are getting from the n minus 1 layer, whatever we are getting, we are adding them and doing a summation over them, and we are computing the nmi. So if we you will see if we compute if put the values of nmi in the equations. So this is if we basically this value we are trying to compute in terms of sensitivity. So we are basically replacing this with respect to nmi. So if we replace it with nmi, this is what we get. Basically chain rule, we are following the chain rule of derivative, and after this we are finding out that this is basically how it looks like. So sensitivity, this is sensitivity as we defined earlier, and this is something that we get if we do derivative on this. This is what we get because this is the value of n. we know. So if we do derivative with respect to weight, so we get the coefficient that is multiplied with the weight. So we get this, and yes, if we do the same for bias, we only get the sensitivity, and then this is how we update the weight with respect to the sensitivity, and this is the final formula that we use to compute the new set of weights and biases using our sensitivity parameter. So in vector form, it looks like this. Basically, whenever we are denoting with some bold character, it is a vector of weights, matrix of weights, and a vector of biases. So this is how the sensitivity is computed with respect to the whole overall weight matrix and the uh, bias or the activation function. So this is the final formula for the mth layer. What is the sensitivity? Sensitivity of mth layer in the neural network with respect to its output. What is so this is how we compute that, and based on that, how do we update the weight values using backpropagation? And this is how you update the values using backpropagation. So if you see here that these are these are denoting the how we are updating the weights in each iteration. So basically this is showing the whole overall picture of the neural network. So via forward pass, this is how we are computing at each layer, how we are computing for every input, how we are computing the output, and this is at nth layer. After we pass it through the activation function, we what we get. And while back propagating, we basically compare that with the function targeted input, and with respect to that, whenever we have to update it, we are updating with respect to the sensitivity. So we are not using that loss function. Instead of that, we are using the sensitivity parameter that is basically showing the sensitivity of mth layer with respect to that loss. As we change the weight and bias, how sensitive it is, how the loss function is sensitive if we change the loss and weights and biases of this particular layer. So accordingly, it is updated, and this is how it is completes its updation throughout the mth layer to first layer. So this is a brief introduction about NN. So the model of the story is basically NN can learn if we have a super data set, or if we can in a semi supervised way, we can show it all the possibilities. It can learn from that as well, uh, and obviously we can manipulate the loss function so that we can train it as we want it to train, want it to learn. So if we see, this is an overview of how we can use this neural network to predict any function. So basically, we know what is the desired output, and we know what the neural network is giving us output. So we are basically using that to train it, and once we have it, so we are basically finding out at an error. So that error is basically what we are using. We know how much we have to adapt based on the error, and this is an idea that we will be going to use while we design controller using neural networks. So we'll see going forward how we are using that idea. So this is how an overall NN control system looks like. So this is a deployed plant, the plant that is running a physical plant. Maybe it can be a vehicle, it can be an industrial control loop, it can be anything. So we are sensing the measurements and giving that sense the measurements as input to the controller that is made with the neural network, and it generates the control inputs, and we sample those control inputs. So this is how it works. So obviously we can train them in different ways. One with supervised learning, other way of doing it is imitation learning. So so this is an important overview of what we are trying to do. Yeah, there are semi-supervised learning as well. We can use reinforcement learning. Reinforcement learning is one kind of semi-supervised learning that we often use. Reinforcement algorithm that we often use to train controllers like this. Basically, we have a we run the controller that we want to train with a modeled plant, along with the noises and the errors that can come in the real world environment. We try to model them as much as possible, and we train the neural network with that in closed loop so that it learns how to control the system, and basically estimate the return, that is the overall reward along the trajectory decided by the current policy. So this is how the reinforcement learning algorithm works. So policy means nothing but how, based on what input, what we are getting as an output. So this policy, I mean, how we are computing the output from the input. So that, if that we call that a policy, so it basically estimates a return, that is overall reward along the trajectory, uh, if we follow this policy and improve the policy to optimize the reward. So basically, again, we are trying to find out if we modify the policy. Modifying the policy is similar to modifying the weights and biases of this neural network. And if we do that, how much change in the uh, return is happening. Again, remember that return is nothing but it is estimation of what is going to happen next if I follow this policy for a certain number of time periods until I reach my goal or something like that. So we can define that, we can decide that. So usually we can decide when it should reach a goal, whenever it is trying to reach a goal or whenever it is trying to achieve something. So up to that, we are trying to find out that what is my overall return for that overall period. So generate samples by running the policy, and then again estimate the return, and then accordingly update the policy. So like that, it keeps on running. So there are a few examples of such controllers. Fixed stabilizing controllers, how does it look like? If we see, it is basically uh, using an inverse plant model, something called an inverse plant model. So what is an inverse plant model? So basically it is learning how the plant is working. Okay. So basically the NN is trained with desired trajectory as inputs and the stabilizing feedback control as loss to be minimized. Okay. So it is trying to minimize some loss, and that is related to how stabilizing the control input is. It's not that stabilizing. If it takes from the if it takes over from the stabilizing controller by making the feedback control 0, if NN is trained, then it takes over. So basically here, if you see, he is the actual plant and this is the plant output, and we are using that output with a stabilizing controller, and as a stabilizing controller is giving some input, so this adaptation algorithm is sending that to an based inverse plant model. And the inverse plant model is basically, plant it basically takes some control inputs and generates some measurable states. So inverse plant model does exactly opposite of it. Basically it takes the stabilizing control input and basically finds out that what is the correction that it needs to add. So as it is being trained, less correction we need to add with the stabilizing controller. So eventually when it is trained, because we are sending the input here as well, well, input means the plant measured plant output that we are sending to the stabilizing controller. So with that input and finding out that with this stabilizing control, this is how it should compute its output when it is trained. So it basically learns when to how to produce the stabilizing control input, and the role of stabilizing controller becomes less and less eventually. So adaptive controller is another kind of NN-based controller. If we use adaptive controller in the loop in this case, so what happens? So we have a plant, and again, so the this plant output is being sent to the NN-based plant model. Along with that, the inverse plant model. So NN-based plant model is taking the input, and it is trying to estimate how the plant is behaving. So it is trying to find out from the value that the actual plant is producing. It is adding its own value and it's sending that to the inverse plant model, so that the plant model can find out what is the correction in the input that it has to produce, that this NN-based controller has to produce, and adding that while the NN-based controller is sending some input to the plant. So there is a reference model from where it is basically learning. Reference model is nothing but uh, it is basically trying to find out with the common control input what should be the current reference output. So if the reference output, if the plant output is matching the reference output, we have to control it less. So that is eventually it is trying to reach this reference output only. So it is tracking, basically trying to track that reference output. So adaptive critic is another different way to design such a system. So here we can have a critic network. That critic network will criticize the actions taken by an actor network, and then the actor network will basically introduce controlling produce control inputs to be to feed it to the plants, and based on the plant outputs will understand, the critic will understand how well the plant is behaving. Observing that, it will understand how much the actor network should be trying to improve. So there are different ways to design them. We'll come into those. uh, so basically limitations, if we think about their limitations, so they are not generic again. So this is the main limitation that we will see. So they will always work best for the system that it is being trained for. Okay. So, and obviously they will not provide any stability or safety guarantee. Especially safety guarantee is very crucial when you are trying to deploy such NNBus controllers. And yes, noise is another issue. So how do you overcome that? Data driven, safe and optimal NNBus control. How do you overcome that? We overcome that by designing something like this, where we have a system and there is an NBus controller, and how do we, this is basically the overall dynamics of the uh, closed loop. So what are we doing here? We are trying to find out, basically let us start by defining this tuple. This tuple is having four things. So F is basically the flow equation that the dynamical system follows, and Gx is basically the input function that how you sense the states, and based on that how do you compute the inputs. And obviously we are considering the system is locally Lipschitz, and this is the feedback control function that we have defined here. So this is basically the domain of the system, dynamical system, and this is basically the input space of the dynamical system from where we are getting the, and obviously these are in the real number territory, in the real domain. So both of these are in real domain. So depending on if the inputs are discrete inputs, like if integer inputs are expected, then this can be in an integer, it can be in integer domain as well. So anyways, what I'm trying to say is basically the system safety, if we want to motivate the controller to remain maintain safety or maintain stability, then basically we have to train it like that. So for that we need to modify its uh, loss function. And how do we modify that? So we use CLF and CBFS ideas that we had earlier, we learned earlier. We use them to penalize or to reward this the policies. I mean, while we are training these neural networks. So if you see the loss function, this is how we modify the loss function. In this case, SD, SI, and SU. What are these? Basically, these are generated from the sampled grids SI, SU, and SD inside XI, XU, and XD. These are continuous domains. So this is after discretizing them with certain uh, granularity. So basically, consider that if this is a overall, uh, consider that this is a, I, so if you have a two-dimensional system, so this is basically x1, this is x2. These are your two states. So this and this, this is real. Basically, this is in So basically, when we are finding out SI, SU, all these things, basically we are discretizing. This can be some delta that we will be using. So we are discretizing in that length. So this is delta 1. And this is basically delta 2. I mean, sorry, this should be delta 2, this should be delta 1. So this is the granularity that I am trying to follow while I am designing them. So now this is how we are designing SI, SD, and SU is basically same thing for maybe U1 and U2. There are again here with a granularity you are considering multiple values, and that is the discrete how you define them in a discrete way. So using them you are defining the loss function. So this first part of the loss function is basically to impose a positive penalty to the sample data points and so that that violates the CBF, and this is basically this part is basically for stability, to maintain the stability. So these where the as we reach the equilibrium point, as we progress the equilibrium point, so less loss, I mean as we approach to an equilibrium point, that is XE, that we define as XE, as we approach to the equilibrium point, we have less loss value that is added to this loss function. And now if we define each and every term here, so this is how it looks like. So if we are using that ReLU activation function here, and what is NB? Let me see. So neural network-based controller that we are naming it with this basically neural network-based function approximator that we are naming as NB. That is basically trying to approximate the CBF for safety. This is for safety. So yes, and what else? NC is another part of that. So this is designed to another function approximator is NC. Let's see what we are doing with NB first. So L1 is part where what so there are SD, SU, and SD and SU. These two things along with that, yes. So this part is basically imposing positive penalty to the sample data point that violate the CBF. So L1 how is it defined? For all X in SI, such control inputs SI is what? Let me see what is XI. XI is what? So initial points, okay, and this is basically XU is unsafe region and XD is domain where we want to be in, okay, and this is how F is defined, this is how G is defined. So U is basically a valid set of inputs that we can take from the allowed set of inputs. So if you notice here, for all such initial points, NB plus epsilon I is basically how this is being calculated. So how did ReLU function work? If you remember, try to remember that. So it basically considers that all the values that is positive, it considers those values with a slope obviously, and it suppresses all the negative values. So it, that is why we are using that ReLU as an activation function to design this first. So what we are trying to do is, if the values are if the values are negative, so it is always adding some positive value as it is approaching. So since it looks like this, so if this is 0, this is how it looks like. This is how it looks like. So with this, we are imposing more and more loss when we are going outside this region. This is basically replicating CBF, remember that. So when going outside the safety region, it is basically in this initial region, basically it is basically imposing some penalty. And same thing for L2. What is L2 doing here? L2 is taking care of this part where I am not safe. This is basically sampling the unsafe region. So whenever the opposite happens, whenever this is increasing, so this is increasing, meaning and negative of NB is basically whenever outside in the in the unsafe region, when I am checking that the CBF, this basically consider this as a CBF, consider NB as a CBF. So how do we design a CBF? So CBF is basically, what does it ensure? It ensures that inside the domain, inside the valid domain, it will always remain negative. Is a safe area. This is something like XD. We have an XI here. So with that, what do we do? Now this whole area is basically XU. So here, whenever we are going towards XU, it should be negative inside. It should be negative inside. It should be positive outside. So it should be increasing. That is what we are taking care here, taking care of here. And it should be in the unsafe regions. It should not be it should not be going to unsafe regions. That is why whenever it is going to unsafe regions, we are imposing more and more loss. And L3 is there for the third property of CBF, that ensures that it should be negative. So basically, if this is negative, then basically then we are imposing. If this is not negative, if this is positive, then we are imposing a loss. So whatever the criteria CBF has to fulfill, the opposite criteria of CBF, if we are going, if we are having some criteria that CBF is not supposed to obey, then we are imposing some, incurring some loss. And that is how we are ensuring that the neural network learns to produce such inputs that will abide by the CBF. And same thing for stability. This is for safety. And this is for stability. Here, what do? We basically try to find out with this. We have the flow function for the dynamical system. With this input, we compute the norm of the output. With this input, whatever input output that we get, and this has to reduce, considering that this is what we are trying to achieve. As less this is, more stable we are. So if this is high, then we are imposing high loss, and if this is low, then basically we are imposing less. And same thing happens here as well. For all x equals to xc, This is what we are only ensuring that this is what if it is again doing the same thing basically. If it is going further, if this is defined for different values of x, basically these two parts L4 and L5. One part is for those x's which are in domain but which has a difference with the equilibrium point greater than epsilon 6, and this is for the when the x is in equilibrium. So these are the x values. So this is a constant penalty that you will keep on getting if you think that when I am reaching the equilibrium. So after we design the neural network based controller with these motivations, if we update the loss function with these motivations, then obviously we will get something where I will be able to maintain safety and make the system stabilized while I am controlling the system using my neural network. So can approximate NC and NB by verify the. So yes, so we have to definitely ensure safety of this neural network via verification, because even though the training is happening based on how you are designing the reward functions, it might not be safe. So to maintain safety, we have to ensure that it is safe while the system is running. We have learned how to verify the system using reachability analysis and SMTS verification. We'll do the same in this case. We'll just approximate this. These consider this is a neural network, right? So we can approximate this as a polynomial. We have the activation functions we know, and we know the weights and biases after training. So using that, we can express them as a polynomial. So using that, we have to verify the overall system is safe while it is operating under the control of such an NN-based controller. So this is an example of such a controller. So it is trying to uh, find some unsafe counter examples using this is what CBF asks you to be in. And if it finds a counter example somewhere outside, it is basically used to rectify the neural network eventually later. So this is how we design a neural network based controller, and this is basically a brief idea using the concepts that we learned earlier. So let's see some problems on this topic. So which one is true for above adaptive controller? So as tracking error, so let's see the setup here. So there is a plant, some disturbances are coming in, and there is a neural network based plant model, and there we are basically whatever output we are getting from the plant, we are comparing that with the NN plant model, and we are sending that anywhere. Yes, we are sending that to the inverse plant model, and with that the inverse plant model is telling me what is the noise and disturbance at plant output basically. Yes, so this will be n-based plant model is not modeling the noise, so whatever deviation that is happening due to the noise, that should basically practically come here, and the inverse plant model is basically trying to find out with what change, how much should I change the input so that I can achieve some control output as desired. So it is adding that to the neural network based controller's control output, and the plant output is also being sent to compute the tracking error, and the tracking error is being fed to the neural network controller following an adaptation algorithm. Maybe we are modifying the loss function or some other way we are updating it, updating the neural network based controller, training it. So, and yes, whatever the command input is, it is also going to the reference model, and it is also producing a reference output, and we are always computing the difference with the reference output. That is what we are computing as a tracking error and sending it to the adaptation algorithm, and following that algorithm the neural network based controller is being updated eventually. So this is how the whole overall framework is working. Now in this framework, what is true among these options? Let's find out. As tracking error increases, the controller becomes accurate. So this is obviously wrong, because tracking error is, we are supposed to reduce the tracking error, right? So tracking error decreases, the controller becomes accurate. This should be right, because our goal is to reduce the tracking error. Our goal is to reach the reference model. right? So next one is compensation for noise characterizes the error in the output caused by only the process noise. So it might not be only process noise, because there can be sensor noise as well. It's very it is visible that it is wrong. Compensation for noise characterizes the input required to reduce the error in the desired output caused by sensor and process noise. This is right. So this is very straightforward. Question 2, which of the following should be true in order to design a safe controller using M? So we just learned about it. Should penalize the agent for generating such control inputs that change the future state such that control barrier function becomes negative inside the safe region. So is this true or false? What do you think? If you try to remember how CBF works, it is always trying to maintain a negative value while it is inside the safe region, and when it is outside the safe region, it is basically having a positive value. So that is how it is differentiating between safe and unsafe regions. That is the crux of designing a CBF, and that is what is being stated here. So I think this is true. What else is in there? You should you should penalize the agent for generating such control inputs that change the future state such that control barrier function negative inside the safe region, and should reward the agent for generating such control inputs that change the future state such that control barrier function becomes negative inside the safe region. It is just opposite of that. No, not opposite of that. Basically, I am asking that you should penalize for being negative inside the safe region, or you should reward it for being negative in the safe region. Yes, these are basically opposite of each other. So in this case, which one should be right? Again, here also I think there are two opposite versions of the same statement. Should reward the agent for generating such control that change the future state such that the rate of change of control barrier function becomes positive inside the safe region. So if it's positive, remember that it will eventually end up having a positive value inside safe region. So should penalize the agent for generating such control inputs that change the future state such that the rate of change of control barrier function becomes a non-negative inside the safe region. So if you see, B and D should be right, because obviously you should. Why B and D should be right? Because if I don't reward the agent for maintaining negative values inside the safe region, my controller will not become safe. And if I don't penalize while doing so, while achieving so, it should always reduce the value of CBF. If it's not reducing the values of CBF, then I should penalize it. It might achieve this, but sometimes it may be increasing the, it may take some control, produce some control inputs that is basically increasing the value of CBF while inside the safe region, that may eventually lead to some unsafe state. So we'll try to avoid that. For that, we'll penalize it. So for stable NN based controller, which of the schemes will be useful? So here also should penalize the agent for generating such control inputs that change the future state such that the eigenvalues of discrete time closed loop state transition matrix approach 0 inside the state space, and should reward the agent control inputs such that the state transition matrix approach 0 inside the state space. We should reward or penalize, that is what we are asking. So the second part of the question is basically, should reward the agent for generating such control inputs that change the future state such that the rate should change, the CLA becomes negative around the equilibrium point. And another is, we should penalize the agent when it produces a control input so that the change of CLA becomes negative around the equilibrium point. So should penalize or should reward? So first thing, again, if we want to maintain stability, we will try to reduce the eigenvalues. If you consider discrete time eigenvalues, basically state transition matrix eigenvalues of the discrete time to state transition matrix should be within the unit circle, right? So in this case, if we reduce it, if it is near 0, then there is very less change among the states, and the states are basically reaching some steady uh, equilibrium point. So that is what we are trying to get. So we'll reward such actions, and while doing so, if I am, if sometimes it is doing this, some it is doing taking some actions, but the CLF is becoming negative around the equilibrium point, then either we can reward it for taking such actions. So if CLF is becoming negative around the equilibrium point, basically that is good for me, because that is decreasing the CLF and sending it to a zero value as I am reaching the equilibrium. That is a good thing. So these two should be the correct answer. Yes. So question 4 here, find out the values passed to the input layer following the terminology used in week 10 slide when the input state vector is this. So we know how to compute this. This is very straightforward question. So how do we define n? N is basically set of weights multiplied by inputs plus bias. This is the whole n value, and when it is passed through the activation function, it becomes a. That is the terminology that we used. So in this case, in this equation, we have to just put the values of the weight matrix that we can get from here itself, and that is given, I think. Okay, if we are given the state matrix values, I forgot to paste them here, I guess. So if you have the state matrix values, weight matrix values, you can use those values. These are the weight matrix values, and you can compute the output accordingly, and these will be the output. So these are very straightforward questions. Such questions can come to clarify you if you understood what we are trying to do here, how the NN is working. So sensitivity of the squared loss function of an NN with respect to its net input of mth layer Nm can be Nm, remember that. So this is N1 for first layer, W into P plus B. So Nm is basically Wm into so the Am plus B. So Am minus 1 basically what we got as output from the last layer. Anyway, so this is the sensitivity parameter, and that this is the definition of it. Now if you break it down with following a chain rule, this is what we get, and from this we can get this. Basically again we are breaking it with chain rule, and these three things can be expressed as how. So this is sensitivity of MI. So basically we are trying to find out recursive formula of SM like we saw in our slides. So if we try to find out what should be in the blanks, so here we should get weight, because we know n equals to W into how do we compute n? Nm plus 1, Wm into Am plus Bm. So here we'll get, if we do derivative on n with respect to Am, we get this, and again this will be basically leaving me with the activation function only, because Am is computed uh, using the activation function that we have for that layer, and this is what we will get. So yes, these are a few questions on this week's lecture. In the next lecture we will see how to we'll go through the some problems on Kalman filter and whatever is there in the next lecture. So thank you. If you have any questions, you can ask. Okay, else I'll finish this meeting. See you in the next class.